Good morning, or good day, or good evening to everybody here in the room and online. Welcome to this session on target speaker detection, localization and separation, which is chaired by Sebastian Braun from Microsoft and myself, Reinhold Heb-Umbach from Paderborn University. We have 5 talks today, of which I think it's the second one will be online, but the other 4 will be here on this stage. And I welcome the first presenter, Katerina Zmolikova, giving a talk on auxiliary loss function for target speaker extraction and recognition with weak supervision based on speaker characteristics. Katka, please.
Thank you for the introduction. Hi everyone. So today I will present our work about auxiliary loss function for target speech extraction. This work was started at the Fred Jelinek workshop in 2020 in collaboration with colleagues from NTT, JHU and CMU. The work addresses the task of target speech extraction and recognition. As you probably know, the performance of ASR system deteriorates a lot in presence of interfering speakers. One possible way to tackle this is to apply target speech extraction to remove the speech of the interfering speakers. In target speech extraction, on the input we have a mixture of multiple speakers, and the desired output is the speech signal of the target speaker only. To determine who is the target speaker, we additionally have an enrollment utterance spoken by the target speaker. The estimated speech then can be decoded by ASR system, hopefully better than the original mixture. The target speech extraction methods today are mostly used on neural networks. These neural networks are trained with loss functions that measure the discrepancy between the estimated target speech and the reference target speech. This loss function could be, for example, mean square error or SI-SNR. However, these loss functions very often lead to too aggressive removal of the interference, and as a result also distortion of the target speech signal. Such signal with these distortions is then not very suitable as input for ASR system. Also, these loss functions require strong supervision. So for each pair of mixture and enrollment, we need the exact reference target speech signal. This is almost impossible to get for real mixtures, so these systems would be typically trained on artificially mixed data, which creates some mismatch if we want to apply them on more realistic data in the end. In this work, we explore an auxiliary loss function that can be used to fine-tune the target speech extractor. The loss function is based on speaker characteristics. It composes of 2 parts, speaker identity loss and mixture consistency loss. In the speaker identity loss, we take the output of the speech extractor and we compare it with several other signals from the target speaker. We would like to compare it in terms of speaker characteristics, so we try to quantify how similar the speaker information is in these signals. So basically, this speaker identity loss should try to force the target speech extractor to extract the signal of the correct target speaker. However, this by itself leaves basically too much freedom to the output because with this loss function, the system could basically learn to output any signal that has the correct speaker characteristics. So to constrain the output more, we combine it with the mixture consistency loss, where in the mixture consistency loss, we extract signals of all the speakers in the mixture, and we check that they sum back to the mixture. The final loss can then be obtained as sum of these 2 parts with optional weights. This loss function leaves a bit more freedom to the output since we don't really compare it with the strong reference, and we observe that it leads to less distortions of the target speech. Also, the only reference that we need to compute this loss function are these other signals of the target speaker. If we have a data set with speaker labels, we can just find other signals of the same speaker, and you will see later that in our experiments we aimed towards long meeting-like recordings, where if you apply diorization, you can just find other parts of the long recording where the target speaker is speaking and use it as this reference. So far, I described the loss in rather high level, so now I will try to go in a bit more details. So in the speaker identity loss, again, the goal is to compare the extracted signals with the other signals of the target speaker in terms of speaker information. For this, we use concepts from speaker verification, namely X-vector extractor to extract speaker embeddings, both from the estimated signal and from the other reference signals of the target speaker. Then, to compare the estimated X-vector, the speaker embedding, and the reference X-vectors, we use PLDA. PLDA is a generative model that is very often used in speaker verification, and it can provide us with the likelihood of the estimated X-vector given the reference X-vectors and the hypothesis that they are from the same speaker. This is something that here we want to maximize, so we formulate the loss function as negative log likelihood. The mixture consistency loss is then much more simple. In the mixture consistency loss, we extract the signals of all the speakers. Here I have example of 2 speakers, but there can be more. We extract the signals of all speakers and then sum them and compare this sum with the original mixture using mean square error. Now I will try to explain a bit how we test this loss function, how we design the experiments. We have 2 data sets. The first data set are mixtures simulated from LibriSpeech data, so this is artificial training set. In this data set, what we have available are the mixtures, also the single speaker references, since this is artificially mixed, and we also have the speaker labels. The second data set that we have is a more realistic test or adaptation set, for which we have used LibriCSS. LibriCSS is a data set which is also based on LibriSpeech data, but the mixtures here are created by retransmitting the data. The data set is designed to kind of simulate meeting-like recordings. So these are long recordings which are not fully overlapped, but there are only partial overlaps. With this data set, again, we have the mixtures, we have the observed speech signal, and also we have speaker labels, or we can obtain them by applying diorization. What we do not have in this data set are the single speaker references. Our experiments then go in 3 steps. First, we train a speaker beam. Speaker beam is the model that we use for target speech extraction. I didn't mention that. We train speaker beam with conventional supervised loss, MSE in our case, on the artificial training set. This then serves as our baseline. In the second step, we fine-tune speaker beam with the proposed weakly supervised loss, but still on the artificial data. And then in the third step, we further fine-tune speaker beam with the proposed weakly supervised loss on the target realistic data. Here, this second step is not really necessary. If we directed it the third step, we would get the same or very similar results. Why we do the second step is that we wanted to split the part of the improvement that comes from the adaptation on the realistic data and the part of the improvement that comes just from different properties of the loss function compared to the conventional loss functions. The results that I show here are word error rates from automatic speech recognition system, and there are 2 columns, all which is average result over the entire test set of LibriCSS. In the test set, there are different recordings with different ratios of overlap from 0 to 40%. And then the second column is the subset with the highest percentage of overlap, which is 40% of overlap. First, let's look at the baseline. So speaker beam can improve the ASR performance, especially in the highly overlapped case, where we can improve from 41% word error rate to 33% word error rate. Then, if we fine-tune the model with the proposed weakly supervised loss, we can further improve by 2 to 3% absolute. Here I would like to emphasize that here we fine-tuned the baseline model, but we also verified that if we train the baseline model longer with the original loss, even with different learning rates, it doesn't improve further. So the baseline in the row 2 is fully converged, and the improvement truly comes from the different loss, not just from training it longer. If we then further fine-tune with the proposed weekly supervised loss, but now on the target realistic data, we further improve, although here the improvement is already smaller, up to 1%. The results that I showed before, these were obtained by using Oracle diorization. The diorization is used at 2 places. First, by the ASR system to define the segments that the ASR system decodes, and second, by the proposed loss when we adapt on the target data to find the other reference signals of the target speaker. Here we also experimented with some diorization obtained by real diorization systems, RPN, Region Proposal Network, and Target Speaker VAD. Here I show only the results on the overlap 40 condition, the highest overlap. And this first part, the Oracle one, these are the results that you have seen on the previous slide with the baseline speaker beam after applying the loss still on the artificial data and after applying it on the target realistic data. And here basically what I would like to show is that with the real diorization, the trend is very similar to the original diorization. Like here you can also see the bigger improvement and the smaller improvement. The numbers with the real diorization are overall worse than the Oracle one because also the segments for the ASR system are defined by a bit wrong diorization. As a final experiment, we also did some analysis of the 2 parts of the loss and how much they contribute to the performance. What you see here on this image is the word error rate as a function of iteration during the adaptation. And the different lines are different weightings of the 2 parts of the loss function. If we weight them equally, 0.5, 0.5, then that leads to the best performance. If we change the weights a little bit, then the performance still stays kind of similar, although a little bit worse. But what is mainly interesting is that if we go to the extreme and we completely turn off one or the other part of the loss, then it doesn't really work, it diverges. So both of the parts of the loss are important, and we need to use the combination of the 2 parts of the loss function. Finally, I would like to conclude and quickly summarize what the work is about. So we explored an auxiliary loss function for target speech extraction that is using speaker characteristics. We observed that this loss function leads to less distortions of the target speech and as a result improved ASR performance. Also, the loss function uses only weak supervision in form of the speaker labels, so it's possible to adapt on some target data where we don't have the reference signals. And although I presented this loss function as a loss function for target speech extraction, it would be actually applicable in the very same way also to speech separation. It's just not something that we experimented with in this work. So thank you for your attention, and I'll be happy to answer questions.
Thank you very much, Katka. So the floor is open for questions. Well, to break the ice, then I start with the first question. About this weakly supervised loss with the x-vectors. Don't you have to propagate then the gradient through the x-vector extraction? How does it work?
Yes, so through the x-vector extractor itself is also a neural network, so that's not a big problem. Just we also need to backpropagate the loss through feature extraction for the x-vector extractor and even STFT, but with today's toolkits it's also possible to do that. And then also the computation of the loss by PLDA is something that you can backpropagate through quite easily. There are no very difficult operations that wouldn't be differentiable.
Okay, thank you.
Hi, thank you for the presentation, very nice. I have one question. I understood that you pre-train with the conventional loss because otherwise there would be too much freedom, no? You would not train using just the speaker. So did you try, I mean, why did you choose that strategy instead of using also the mean square error loss in the training?
You mean training from scratch?
Using 3 losses, yes, instead of pre-training and then adapting.
Using both of them as a multitask loss, you mean?
Or the combination of the 3 losses, mean square error, mixture, and speaker, instead of pre-training and then adapting. I don't know.
Yes, so that would be possible. So one thing is we tried to train from scratch just with this loss, but that doesn't really work well. The loss has like too much freedom. For like the multitask loss, we haven't tried that. We just assumed having the pre-trained model, we had it available. But I think that that would be possible and is also, I think, a good strategy to do this.
I have a few online questions. The first one by Ryan Heilman. Do you have word error rate numbers for specifically non-overlap data as well with this loss?
Yes, we have them. And they improve quite significantly. So actually, like these conditions with very low overlap, these do not have very good results with the original speaker beam, and with this proposed loss, they improve quite significantly. But overall, all of the conditions improve. I think I don't think we have them even in the paper because there was not enough space, but you can just write me email, I can send also these results.
Okay, and another question by Piero Perucci. You said it is applicable to speech separation. Do you mean without having target speech reference data?
So still we would need to somewhere get the reference signals of the target speaker. But again, if we aim to this condition of the long meeting-like recordings where we apply the diorization, we can still get these reference signals and use also for training of speech separation.
Okay. More questions here from this audience? Then there is a final question, because I think Shankar Mukherjee liked your slides. Is the PowerPoint available?
It's Beamer, but again, if you email me, I can send the source code, although I don't think it's very nice.
Okay, so thank you very much.
Thank you very much.